Welcome to this video on the thermodynamic behavior of desiccant systems. In this lesson, we'll explore how air behaves when it comes into contact with desiccant materials, both under ideal and real-world conditions. We'll follow the air paths on the psychrometric chart and analyze what happens inside the desiccant structure during operation and regeneration. In this video, we'll explore three key aspects of desiccant thermodynamics. First, we'll describe the fundamental processes of sorption and desorption. Then, we'll interpret how these processes appear on the psychrometric chart. And to conclude, with a discussion of how real systems deviate from the ideal case. After completing this video, you'll be able to interpret the psychrometric behavior of air during desiccant dehumidification, and you'll also be able to recognize and explain the deviations that occur between ideal models and the actual performance. Let's start with a question. Think about the time when you walked into a building and the air felt distinctly dry and even a bit warmer than outside, perhaps in a museum, a library, or a lab. Now ask yourself, could a desiccant system have been used there? What do you think happened to the air before it reached your skin? Did it lose moisture only, or also heat? Did the system add heat as a side effect of drying? Let this question guide your attention as we dive into the thermodynamic paths and processes of air inside a desiccant system. Let's begin by looking at this figure. This curve here shows how a desiccant's moisture capacity increases with relative humidity. And here now. On the vertical axis, we have the ratio of water mass held by the desiccant to the mass of the desiccant itself. Then here we see at 100% relative humidity, typically desiccants can hold 20 to 50% of their dry weight in water. The absorption process begins at stage 1, when the dry desiccant is exposed to humid air. Water vapor from the air diffuses into the pore of the desiccant structure, increasing its moisture content to state 2D. Regeneration begins at stage 3, where the desiccant is exposed to hot, dry air. This air picks up the retained moisture and brings the desiccant back to a low water content at state 4D. This cycle allows continuous dehumidification using thermal energy. In this figure, we can observe the path that the air follows during desiccant dehumidification. The processed air enters at state 1, warm, and here is warm and humid. As it moves to state 2, and this here is ideal, we see a reduction in humidity ratio but an increase in dry bulb temperature. This behavior is explained by the heat of sorption. As the desiccant absorbs water vapor, it releases heat. This warms the desiccant surface, which in turn transfers heat back into the air stream. Because this transformation doesn't add or remove heat from the system overall, the enthalpy line is nearly constant. See here, it follows the constant enthalpy line. It's essentially the reverse of evaporative cooling, where air is cool but gains moisture. Now let's look at the regeneration stream. It begins at the stage 3 with hot dry air. As this air passes through the desiccant, it picks up moisture and becomes cooler and more humid, ending at the state 4. This step is essential for removing water from the desiccant and restoring its drying capability. This figure shows the more realistic cyclomatic paths for both the process and regeneration streams. The process streams enters at state 1 and ideally should reach state 2 ideal here, but in reality it exits at state 2 here with higher humidity than expected. This deviation occurs because moisture and heat do not move instantly. Two waves, as a fast one and a slow one, travel through the desiccant matrix. The air that exists between these waves is our desired product, dry and moderately warm. To optimize performance, systems often purge the air that exists too early, and rotation speed is carefully controlled so that the desiccant enters regeneration before becoming saturated. Despite these controls, non-uniform flow and imperfect transfer cause the outlet air to fall short of the ideal condition. In this video we saw, some key takeaways about this video. No? Here we saw the absorption processes heat air and regeneration, cools and humidifies it. No? So the air paths in a cyclomatic chart are close to constant enthalpy, behaving opposite to evaporative cooling. Finally, we discuss how real systems introduce deviation due to lagging temperature and humidity waves. Now that you understand the thermodynamic behavior of desiccant systems, you may want to investigate how they are integrated into complete HVAC air loops. Controlling rotor speed and regeneration conditions is key to system efficiency, a topic worth diving into. Finally, compare desiccant systems with alternatives like cooling-based dehumidification to assess when and why they are preferred. Thank you for watching this video.